This is the second part of phases of matter, which means the solid, liquid, and gases. And in this part, I will talk about the properties that are due to intermolecular forces. I mentioned last time that intermolecular forces are very important in determining whether something will be solid, gas, or a liquid. But there are also several other properties which are due to intermolecular forces. So some of those properties are going to be vapor pressure, boiling point, freezing point, surface tension, viscosity, adhesion, cohesion, and solubility of substances. So you can see that intermolecular forces are really very important in our life and in determining physical properties of substances. We'll start with vapor pressure. So the vapor pressure of any substance is going to be the partial pressure of the vapor over the liquid at a particular temperature. Vapor pressure is temperature dependent. We'll talk about that again over here. But in any case, right here is where your liquid substance is. And as the liquid substance is just left by itself, then the vapors will start coming out of it. And as they're coming out, they will exert a pressure right on the liquid, and that is called the vapor pressure. So if you have an enclosed system like this, okay, where everything is contained, then these vapor will come back right here and exert the pressure. At one time, what is going to happen is that these will be in equilibrium, which means that the molecules will start evaporating, come right back, evaporate again, come back. That's called a dynamic equilibrium. So you have this constant evaporation and condensation of molecules going on. You can have that even in an open system, but this is more evidenced in a closed system. And that would be called an equilibrium, okay, when you have things going back and forth all the time. So anyhow, let's look at the next point, which is that vapor pressure is dependent on intermolecular forces and temperature. Let's look at temperature first, okay, because this is the easy one. Why so? Because as we know that if you increase the temperature of any substance, then you also increase the kinetic energy of that substance. So once the kinetic energy is increased, then of course the vapor molecules will start moving faster, and if they're moving faster, they exert more pressure. First of all, you will have more vapor molecules, and then they will also exert more pressure on it. Okay, so for example, you can pick any of these substances from here, whether it's diethyl ether, chloroform, or water, but as the temperature is increasing, the vapor pressure is also increasing. Okay, this is vapor pressure on the left hand side. So the vapor pressure is also increasing with temperature, which is pretty normal then, okay, because the kinetic energy of molecules is increasing. The second thing, which is also critical here, which is why we're talking about vapor pressure here, is the intermolecular forces. So as the intermolecular forces increase, then the vapor pressure will actually decrease. Okay, it will not be the same. Why so? Let's look at this. So if you have chloroform, diethyl ether, carbon tetrachloride, and water, okay, these are four substances over here. And water, as you know, the intermolecular forces in water is hydrogen bonding, which is one of the strongest forces, okay, in intermolecular forces. Diethyl ether has dipole-dipole forces. Chloroform, carbon tetrachloride would have forces like induced dipole. Okay, so here we have all the different kinds of forces at interplay. And if you look at a particular temperature, let's say at 40 degrees centigrade, okay, at 40 degrees centigrade, diethyl ether has the highest vapor pressure, okay, and that is because diethyl ether has very few intermolecular forces. And so because of those very few intermolecular forces, the molecules are evaporating much faster. Whereas water, which has hydrogen bonding, has very good intermolecular forces, and because of those very good intermolecular forces, at 40 degrees Celsius, there is not much evaporation going on. Okay, and then chloroform and carbon tetrachloride are kind of in the middle here. So intermolecular forces are very important in determining vapor pressure of any substance. Now, you don't have to know the exact number of what the vapor pressure would be, but you should be able to take 2 or 3 compounds and be able to predict which one will have the highest vapor pressure, which one will have the lowest vapor pressure. So again, the lowest vapor pressure is coming from the highest intermolecular forces. Boiling point is kind of related to vapor pressure, and that is because boiling occurs when the vapor pressure is equal to the atmospheric pressure. So when the vapors that are coming out of any liquid exert the same amount of pressure as the atmospheric pressure, that's when boiling occurs, okay? And when boiling occurs, we kind of all know what that looks like, okay? That is when the bubbles start forming and you know, well, a substance is boiling versus not boiling, okay? You can actually see that. And that is because the vapor pressure exerted is equal to the external pressure, atmospheric pressure. Whether you're at sea level or in the mountains, it doesn't matter. But that would be the temperature at which the liquid boils. So that is the boiling point. And again, because vapor pressure is dependent on intermolecular forces, obviously boiling point will also be dependent on intermolecular forces. So generally what we do is when we give compounds to compare, we don't say compare them in order of vapor pressure. We may also say compare them in boiling points, okay, in order of boiling points. So that is another type of question, but it is very related to vapor pressure, okay? So the same order that you would have for vapor pressure is the same for boiling point, okay? So for example, as in the previous slide where we had diethyl ether and water, diethyl ether would have a much lower boiling point than water because water is hydrogen bonding and diethyl ether does not have hydrogen bonding. It's got weak dipole-dipole forces. The heat of vaporization that is given over here is the heat required to vaporize a liquid, and this is just to give you an idea of how much energy would be required, and of course this is related to intermolecular forces, okay? And so we may not be doing any calculations on this, but in case you see anything in there for a comparison's sake, you know, now you know what it is, okay? And then of course here it's an example of what the intermolecular forces will have an effect, okay? So water of course will have a higher boiling point than hydrogen sulfide, which are in the same group. Surface tension. The surface tension of any substance is created on the surface, okay? And what happens is that when you have molecules that are trying to evaporate, you also have molecules that are trying to pull those molecules back inside, okay? Why are they trying to pull them back inside? Is because of the intermolecular forces, okay? Why are these molecules trying to escape? It's because of the energy differences. The molecules on the surface will usually have higher energy than the molecules inside. Why? Because these are exposed to a higher temperature over here. So this pull and push of forces that's going on will create this kind of a thin film on the surface, which is called then a surface tension, okay? And this is a really key thing and a very important aspect, especially as far as water is concerned. It's a very important property of water, okay, that you have surface tension, because a lot of substances do not have surface tension because they don't have this push and pull. And even if they have this push and pull, it may not be as substantial as it is in water, okay, because water has very high intermolecular forces. Remember, hydrogen bonding. So if you're comparing water with hexane or diethyl ether, if you want to think about that, then water will have a higher surface tension. Why? Because again, intermolecular forces will be pulling the molecules inside, whereas these molecules are trying to escape. So the tension created on the surface is actually very good. And what the surface tension does as far as the property of water is concerned is it allows things to float on water, right, as we know. But then there is also a problem with this, okay, because due to surface tension, things don't dissolve so well in water, which sometimes you do want them to dissolve in water. So for example, when we have to wash clothes or dishes, the surface tension is a big problem because the surface tension does not allow the dirt and the grease to get dissolved in the water. So one of the problems for all the detergent companies is to actually break that surface tension, okay, and allow the dirt and grease to dissolve in water. Anyhow, that is what surface tension is. So again, remember, the stronger the intermolecular force, the higher the surface tension. One of the actions that results from surface tension is what we call capillary action, which are two kinds, cohesion and adhesion. And capillary action is the one that makes you see the meniscus, okay? And we've all seen meniscus before in our labs when we measure in a burette or a grad cylinder. So you've seen a meniscus before, and that is a result of cohesion or adhesion. Okay, so what is cohesion or adhesion? Cohesion is the attraction between like molecules, and adhesion is the attraction between unlike molecules. Okay, so for example, when you have water in a test tube or in a grad cylinder, or whichever glass container, then you will see that the meniscus is like this, okay, like a smiley face. Okay, whereas if you have mercury in a glass container, then it would be like this. Okay, kind of like a sad face, but that's what it would be. And that is because of how mercury behaves with glass and how water behaves with glass. So in case of water and glass, the adhesion forces are a lot more, which means that the attraction between unlike molecules is a lot more. So water is H2O, and glass is made of silica, which is silicon dioxide, SiO2. So which means that the forces between, or the intermolecular forces between water and glass are pretty good. And if they're good, then what you see above this line here is this is the attractive forces between them. Water is never going to be a straight line, and neither will mercury. Okay, there are hardly any liquids that are straight lines. So here is this little curve is caused by this addition. Okay, because the water molecules are attracted to the glass molecules. However, in case of mercury, that doesn't happen. Okay, which means that the mercury doesn't like the glass very much. So the intermolecular forces within the mercury will take over. So you have more cohesion than adhesion, and so mercury looks like a blob. Okay, and which means that it is within itself and not trying to touch the glass that much. Okay, and so these are two kinds of meniscus that occur, and you have not seen the mercury one that much because we don't even have mercury thermometers anymore. But you've seen the water for sure. Okay, and a good place where you can see cohesion is actually in car waxing. Okay, so when you wax your car and it rains, I'm very sorry it rained, but when you wax your car, and it rains, then you will see the water as actually droplets, okay, in there. And so once you see the droplets in there, those drops are actually like little blobs, and those is because the water is being attracted to itself in a very cohesive manner, okay, because water does not like wax very much. Okay, so there's more of cohesion than adhesion going on. So when you have similar intermolecular forces, okay, like in water and in glass, then you will see adhesion. And when the intermolecular forces are a lot more within itself, then that would be more cohesion. Okay, so that is how adhesion and cohesion work, and intermolecular forces. So it depends, okay, what substance is where. And then we have another property which is called viscosity. You will do a lot more of viscosity and surface tension and all of this in physics. Here we talk about the chemical forces. In physics, you actually talk about some of the quantification of all these things. So viscosity is the resistance to flow exhibited by liquids and gases. Now remember, solids are not flowing anywhere. Okay, solids are pretty stable. So we're talking about how the liquids and gases will flow. So for example, here we have two substances, glycerol and water. Okay, and if you throw a little pellet in there, then the pellet will drop much faster in water, whereas the pellet is still traveling in glycerol, which means that the pellet is going very slowly through glycerol, which means that the glycerol is actually preventing the pellet from dropping, and that is because it doesn't provide that smooth passage, okay, which means that there is actually a resistance to the flow. Okay, and this usually happens in syrups. Okay, so for example, if you've ever had pancakes, please tell me you've had pancakes, and if you have syrups in there, then you know that the syrup will flow much thicker in a much slower way than water would. Okay, and the same thing goes for honey. For example, honey is very thick and very viscous, okay, as we say. So that's kind of what viscosity is. And again, viscosity is a property of intermolecular forces. The higher intermolecular forces you have, the higher the viscosity would be then. Okay, and so even though water does have high intermolecular forces, glycerol, which has 3 OH groups, whereas water is H2O, HOH, glycerol is 3 many more OHs in there, and so it has 3 times more the hydrogen bonding, and so the viscosity is very high for glycerol. Here is a nice table of comparing all the different kinds of substances and the different properties that they have. So we've talked about vapor pressure, surface tension, and viscosity. And so here are some substances like water, carbon dioxide. Now water has hydrogen bonding. Carbon dioxide is pretty much a non-polar substance. Pentane is also non-polar because if you look at C5H12, there's hardly any electronegative element. So the only forces in pentane would be, yes, van der Waals forces. Glycerol has 3 oxygens in it, so there's plenty of dipole-dipole forces. And I mentioned before that glycerol also has hydrogen bonding. Then there's chloroform and so on and so forth. So here we have a whole bunch of substances, and then look at the vapor pressure of all of these. Okay, so the vapor pressure of water is pretty low. And then the vapor pressure here, look at for carbon dioxide, is very high. And it should be because it's a gas, okay, in any case. So, and look at glycerol, way low, okay. And that is because of the high intermolecular forces in glycerol does not let any of its molecules escape, okay. So vapor pressure is very low for these. Now you can also use vapor pressure to predict boiling points, okay, of any substances, which means that the boiling point of glycerol is going to be very, very high, okay, because it takes a lot of energy to break these intermolecular forces. Surface tension, almost the same thing over here. Water has pretty high surface tension. Carbon dioxide, as usual, has none. Pentane has almost, like 1/6 of that of water. So it's very low surface tension, and that's because pentane has hardly any intermolecular forces. There is just the induced dipole, that's about it. But water has hydrogen bonding and so on. So, and then look at glycerol, it's almost as good as water. Viscosity, we've talked about that too. Okay, viscosity very, very high for glycerol and definitely very low for carbon dioxide, and then very low for pentane also. It says pentane is very free flowing, it'll pass anything through. So there those are the 3 properties that we've talked about. So it's a nice little table to compare properties. And then finally, let's talk about solubility. Okay, this is an important part of intermolecular forces as well. Your rule is going to be like dissolves like. We're going to talk about solubility more later on also, but I just want to mention it over here also because it's important for you to know what dissolves and what due to intermolecular forces. So your rule is like dissolves like. That is going to be the universal rule forever. Substances with the same intermolecular forces will dissolve in each other. So if you have something with hydrogen bonding and another substance with hydrogen bonding, both of them should dissolve in each other. The intermolecular interactions are going to be between the solvent and solute. Okay, and we will talk about solvent and solute in the next chapter also, but this is really just the 2 substances that you are trying to dissolve. Okay, so again with like goes like dissolves like, a non-polar substance will dissolve non-polar substance. Okay, so for example, we were talking about glycerol and water, okay, before, which both of them have hydrogen bonding. So it is pretty logical that if you try to dissolve glycerol in water, it will dissolve, okay, in there. If you try and dissolve carbon dioxide in water, it's not going to dissolve because carbon dioxide has only got minimum dipole forces, or almost none dipole forces. So which means that carbon dioxide does not dissolve in water, which is evidenced by all the pop drinks that we have, okay, in which they have carbonated beverages, so the carbon dioxide will go away. Some of the other forces that come into play are going to be the ion dipole forces. Okay, and this is true when you start talking about ionic compounds. So when you have water and you're trying to dissolve sodium chloride, the intermolecular forces that are causing sodium chloride to dissolve in water are going to be different than the intermolecular forces that are used to dissolve water with methanol, for example. Okay, and so one of the things that you have to watch out for, if I ask you what dissolves in what and what are the intermolecular forces that are responsible, then you should look carefully at both of the substances and then decide what intermolecular force is playing through. So for example, if you have water and then you have methanol, since methanol, you have a hydrogen connected to oxygen here, this has hydrogen bonding and water has hydrogen bonding. So methanol is dissolving in water due to hydrogen bonding, whereas sodium chloride is dissolving in water due to dipole-dipole forces and ionic forces. Okay, that is what's causing sodium chloride to dissolve. Sugar, I have to give you the structure of sugar, otherwise you have no idea what sugar looks like, and so you can't predict what intermolecular force would be, but I'm telling you now for now, and then we'll talk about it in class also. Sugar has a whole lot of OHs, okay, in there. If there's OH in there, OH means hydrogen bonding, okay, and so therefore sugar also dissolves in water due to hydrogen bonding. So water will not dissolve hexane because there's absolutely no corresponding intermolecular force here, okay, and so if you put hexane in water, you will end up seeing two layers, okay, you will not see one layer. One layer meaning everything had dissolved in it. However, hexane, which is nonpolar, will dissolve ether because ether is very nonpolar. It has little dipole, but a lot of it is going to be the van der Waals forces. So that is how you determine what is going to be soluble in what. And you will have to do this for me. Your key concepts from this one is to be able to predict vapor pressure, boiling point, according to intermolecular forces. You should be able to tell me about surface tension, viscosity, and if I give you 2 or 3 substances, you should be able to compare all those things. You should be able to tell me which substances will have adhesion, cohesion, and then definitely predict solubility of substances, in addition to telling me what intermolecular forces are at play here.